The MMCM uses PLLs for all of these clocking features. It can replace external PLLs to lower your system cost. Now, this slide is pretty much a review from what we've already learned. First of all, again, there's up to 9 CMTs per device, and this will vary by device density. There are 2 MMCMs per CMT tile. There are 2 software primitives that are supported with each MMCM, a base and advanced. The base is the basic port functionality, which is actually most of what people are using. And the advanced provides access to all ports, as we'll get into. There are 8 independently programmable clock outputs, pins 0 through 6, plus the clock feedback out. Note pins 0 through 3 and the clock feedback out true and complement outputs are supported. There are also additional MMCM advanced features, including the clock input switching feature and the phase shift port. Now, the MMCMs are located in the center column of the device. The PLL is designed to remove your input clock jitter. The MMCM advanced primitive supports the dynamic input selection and the dynamic phase shifting features. Now, this diagram shows the internals of the MMCM and helps to explain how these resources work. The first portion shows how the clock switching functionality is built into and allows synchronous switching of the source clocks. Then the output is fed to a programmable counter divider denoted by the letter D. The derived clock is then fed to a phase frequency detector denoted as a PFD, which compares the feedback clock, that's the clock that has been selected, to route back to the MMCM input for clock input compensation. The phase frequency detector accepts an input frequency of up to 650 MHz. The clock input detection circuitry is also found associated with the phase frequency detector, so we can determine if either of the feedback clock or the clock has stopped. Next is the charge pump, and this adjusts the output voltage higher or lower based on the feedback input to the phase frequency detector. The charge pump controls the VCO frequency, which can support up to 1.6 GHz clock. This is then followed by the loop filter and the voltage-controlled oscillator. The oscillator has 8 programmable counters associated with it that allows our desired clocks to be made. Many different output frequencies can be made based on a programmable multiplier and divisor value that you can set for each MMCM. Each MMCM can have its own programmable value. M can range from 1 to 64, D from 1 to 80, and your output from 1 to 128. Now note that the clocking wizard is going to be used to customize the MMCM resources. There are also other MMCM features. Again, fractional counters give you the ability to configure port 0 and the clock feedback out as counters with 1/8 granularity, e.g. 2.125, 2.250, etc. Ports 0 and through 5 counters can be combined together. The clock feedback out and the output 6 counters can be combined. And this enables many more frequencies to be synthesized as you may need. There are 2 methods of phase shifting. There's a static phase shift using the time shift VCO outputs, as well as a dynamic phase shift using the phase shift or PS port to change the phase on the fly in increments of 1/56 of the VCO period. Now please note that as a division occurs, the duty cycle can vary, but the division will be correct. The static phase shift amounts can be set independently on each MMCM output. Using the dynamic phase shift port will adjust the phase shift on all MMCM outputs in addition to any static phase shift amount that is configured on each output. Other additional MMCM outputs include complement outputs for ports 0 through 3 of every MMCM have both the true and the complement outputs available to you. And this will support providing a 180-degree phase shift output. There's also a locked port. This signal shows that the MMCM has locked onto the input frequency. There is also the clock in stopped and the feedback stopped. These are status signals indicating that the input or feedback clocks have stopped running. And there's also a power down port, which is not shown in this diagram. This is used as a disable or enable signal to the regulated supply of each MMCM. Note the unused MMCMs will draw power. The MMCM connectivity supports many possible inputs to each MMCM, either from the clock-capable I/O pins from the inner I/O columns. Note that again when planning your pinout, only the inner I/O columns, the global clock inputs, the BUF-G, or the GTX transceiver clocks that are found from those dedicated resources. The MMCM outputs drive the BUF-G, the BUF-H in the same region, or the performance paths to the BUF-IO and the BUF-R resources that we spoke about earlier. Now note that the ability to drive clock-capable I/O to the MMCM and the BUF-G directly decreases the need for dedicated clock input pins, and this is the reason why we added that functionality. This slide shows you a simple way to deskew your distributed clock. Note that this really means a compensation for the clock's input delay. There will always be some clock distribution skew due to the clock routing resources, so again, just keep in mind we can't take our clock skew to 0 because we don't have a superconducting interconnect, okay? So there's always going to be some. But the key here is we want to be able to compensate for our input delay. Now first of all, you can use a BUF-G on the clock feedback output if a precise phase relationship between the input clock and the output clock is desired. And that's actually a very typical situation. It's the most flexible solution, but requires the 2 global clock buffers. So depending upon your application, if your buffers are at a premium, you may choose not to use a BUF-G in the clock feedback out if you don't care about the relationship. Most commonly, people will remove the BUF-G on the clock feedback out if there is no need for a precise phase relationship between the input clock and the output clock. This is often the case with frequency synthesis or jitter filtering. But in the end here, what's happening is we come in through a dedicated clock pin. That's what's denoted by that iBUF-G primitive. This will drive to the MMCM through a clock input port, and then our output, our desired clock, is routed globally on a BUF-G. And the clock feedback out, like as I mentioned, you could use a BUF-G if you care about syncing up those clocks, and that would be used to feedback the clock to the clock feedback import.